Oh man, are you guys ready for another math review? Yay. All right, so let's see. What do we have to do this week? Well, okay, this isn't exactly math. It pertains to math that we're going to do later, so I want to review this really quickly. It is measurements of the phase of a wave. So, okay, so here's a speech waveform, right? And we're going to, for these purposes, we're going to say that each one ends about here. I have a hard time. I'm gonna have a hard time erasing that, so I'm just going to make straight lines. Okay, so let's get another pen. There we go. So we've got a few things here. Number one, this is time, right? That's our period. So T, we'll just denote that as T, capital T. All right, so that's great. We've got a couple other easy ones in here. So we've got here where the vocal folds are closed to here, we denote that as TC. That means time closed. And then here, where the vocal folds are open, we're going to go TO. That's the time open. And the last two are a little bit more kind of finicky, sort of. So we'll go from here to about here. This is when we'll denote this as TP. TP. We'll call that TP. That means time when the vocal folds are moving outwards. Time when the pressure is positive. Time when their movement is positive. The size of the opening is growing. So the glottal opening is growing. That's TP. That stands for positive. And then this other one is TN. That's negative. That's when the glottal opening is closing. And we're going to use these for computing some other things. I might be able to fit them on the same slide, actually. So the open quotient, Q sub O, is just T sub O divided by T. That's the open quotient. That just means the proportion of each period that the vocal folds are open. So you take TO and you divide it by T. All right, and then we also have the skewness quotient, Q sub S, which is going to be TP over TN. And so there you're looking at the proportion of openness, the proportion of time when the glottal opening is widening to the proportion of time that the glottal opening is closing. And it should come as no surprise to you that if you take T sub P plus T sub N, it equals T sub O. And that T sub O plus T sub C equals T, right? So the time positive plus the time negative is the entire time of that it's open, and the time open plus the time closed is the entire period of the speech waveform. Okay, great. So that's pretty easy. Let's get rid of all this. I wish I could say that I was faster, that I've gotten faster at this over time, but I haven't. It just, I should learn, don't do dotted lines. They're really cool on an actual chalkboard, but You know how often I get to use an actual chalkboard? It's like never. Okay, so we've got jitter. And jitter is frequency variability. Well, let's not put sub n on that. We'll just call it frequency variability. And this italicized F denotes frequency. Also, that's what that is. Like, I didn't do it very well, but that's supposed to be an italicized F. If I actually concentrate on it, there we go. There's F, and then F sub O is your fundamental frequency. So that's what they should look like. The italicized F. Let's, you know what? We're here. There. So jitter is frequency variability. And the frequency for jitter, I mean, not the frequency, geez, what the hell am I talking about? The formula for jitter is going to be jitter, well, actually, we're going to say percent jitter equals the sum of every there we go. The sum of every frequency, every harmonic minus the next harmonic in line over n minus 1. N is the number of frequencies you're dealing with. That's going to be over the sum of every frequency over n. And all that is multiplied by 100. So there's your formula. If you're not super great with math and formulas, that's okay. You don't totally have to understand all of this formula because, again, just like last time on the exam, you're going to have your notes. You'll have your notes of how to do things. Let's run through an example of this really quickly. So if we said that we had, probably should have planned one out. I'm going to have to take some time to draw this. I'll probably just cut it out, and what you'll see is that something has appeared. But for me, it's going to go on forever. So we've got frequency is going to be in white, and amplitude is going to be in red. So we can actually do jitter and shimmer at the same time. The reason why we're going to do jitter and shimmer at the same time is the formula is pretty much the same. So if you look at our formula for jitter, which is right here, if we did percent shimmer, it's pretty much the same thing, only instead of every frequency is what I should put in, I'm going to put in every amplitude difference. Right, over n minus 1. And then it's pretty much the same from there. You just swap out frequency for amplitude, and you're great. You're good. It's the same. So let's run through this once for frequency and once for amplitude. Okay, so this is the period that we have between all these. So we've measured these out. This harmonic peak right here occurs at 0.5, the next at 0.6. There's 0.6 between them. Then there's 0.4 between the next one. There's 0.5, there's 0.5, there's 0.8. So that's the spacing. What we want to know is the difference between those spacings. In a perfectly periodic signal, it would be 0. In a perfectly periodic signal, these would all be 0.5, and there would be 0% jitter. There would be nothing. But that's a perfectly periodic signal, and nothing is ever perfect. So we need to figure out the difference between each one. That's what this part of the formula means. You're going to take every frequency, so 0.5 spacing of the frequency, I should say. So you're going to take 0.5, you're going to subtract f, the next frequency up, right? So f sub n minus 1. I am pausing because what I realized here is that you might end up with a negative in this. So what you actually want is you want the absolute value of that. So it's the sum of the absolute value of the frequency minus the next frequency over n minus 1. N is the number of frequencies you have, frequency spacings you have. You'll see why that's n minus 1 in a second. 0.5 minus 0.6, the absolute value of that is 0.1. 0.6 minus 0.4, the absolute value is 0.2. 0.4 minus 0.5, the absolute value is 0.1. 0.5 minus 0.5, hey, cool, 0. And then 0.5 minus 0.8, the absolute value is 0.3. So now we started out with 1, 2, 3, 4, 5, 6 harmonic spacings, 6 frequency spacings. Now we have 1, 2, 3, 4, 5 differences, and that's why we have n minus 1 on the bottom of that part of the formula. Okay, so we have to sum these. So we've got 0.3 plus 0.1 is 0.4, plus 0.2 is 0.6, plus 0.1 is 0.7. So we end up with 0.7 divided by n minus 1. Again, we had 6. Now we have 5 differences. So n minus 1, there are 6 frequencies, so we have 5. So it's 0.7 divided by 5. I don't know what that is. I have to use a calculator for that. So, okay, it's 0.14. All right, now we want to figure out what is the average spacing here. So we're going to figure out, essentially you just do 0.5 plus 0.6 plus 0.4 plus 0.5 plus 0.5 plus 0.8. And then you divide that by n. You take the average, right? So 0.5 plus 0.6 plus 0.4 plus 0.5 plus 0.5 plus 0.8 equals 3.3, and we had 6 of them. So 3.3 divided by 6 equals 0.55. The last thing we need to do, so now we have 2 parts of the formula, right? Let me highlight these. So we've got this that we've computed here. That's this part of the formula. Then we've got this number that we computed here, the average spacing. That's this part of the formula. Now we need to do what's in there. We need to divide those, right? So we're going to take 0.14 over 0.55. 0.14 divided by 0.55 equals 0.2545. 5. Okay, and then you multiply that by 100, and that's easy enough to do. You just shift the decimal over, right? So you go 1, 2. So now you have a jitter, percent jitter equals 25 point, oh, let's just say 46%. Hooray. So that's jitter. Now let's do shimmer. All right, let's work on shimmer. So just like before, we want to find the difference between each of these amplitudes. That's the first thing we want to do. So the absolute value of 8 minus 6 is 2. The absolute value of 6 minus 6 is 0. Absolute value 6 minus 9 is 3. Absolute value 9 minus 5 is 4. Absolute value is 5 minus 10 is 5. Okay, and again, we started with 6 frequencies frequency spacing, actually amplitudes rather, sorry. And so when we subtract those, we end up with 5 difference values. And that, again, is why we have n minus 1. So we're going to sum these. 2 plus 3 is 5, plus 5 is 10, plus 4 is 14. So we're going to have 14 over n minus 1, 5. 14 over 5 is 2.8. And now the next thing we need to do is find the average of the actual amplitudes. So 8 plus 6 plus 6 plus 9 plus 5 plus 10 is 44. This time over n because there are 6 of them, and that gives us 7.33. Cool. So now what's left is we have to divide this one by this one. 2.8 over 7.33 equals 0.3820. And then you're going to multiply that by 10, so you pop that decimal over by 2 places, and you end up with percent shimmer equals 38.2%. I forget that I can go off the edge of that every time. 38.2%. Okay, so that's jitter and shimmer. Really quickly, I want to show you what you can actually use jitter and shimmer to predict when you do it in the clinic. So I've found some articles that might be interesting. This one right here shows that both jitter, well, it's a little small, isn't it? Let's first let's make sure we're still recording. We are. There we go. So both jitter and shimmer can be used to predict nodular edema or inflamed tonsils. So nodular edema would be vocal nodules or nodes. We've talked about those. If you had my anatomy class, you should know about those. Inflamed tonsils, we talked about that as well. And both of those can be used to determine what's going on there. So nodes and inflamed tonsils are going to bump up your jitter and shimmer values. Notice that our normal value, we've got a table of normal values here. So normal jitter is about 0.5% roughly, or 2/3. And normal shimmer is about 2%. And so anything higher than that, this person right here, you can see that this is actually from a person. This is from someone at the clinic, or at a clinic rather. They've got 1.4% and closer to 4% shimmer. So those are both elevated, and shows that there's something going on. There's all this other stuff that we can measure too. We know that noise to harmonic ratio, they do it a little differently than we do it. They do a noise to harmonic ratio. In that case, a lower number is better because they're putting noise first. The noise is going to be on the top of the equation, and the less noise there is, the lower the number it is. And you can see that this person is right there close to the normal values, right? So they don't have a lot more noise, but they do have more jitter and shimmer. We compute harmonic to noise ratio, and in that case, a larger number is better because the harmonic is on the top of the equation and the noise is on the bottom. So you just kind of got to look at the, got to be mindful of what you're looking at. So it's computed the same way. You just kind of flip their inverse of each other. So if you work at a clinic where they do noise to harmonic, same basic formula, you're just swapping the math that you're doing. Some people look at jitter and shimmer raw values, and that's just, you're not multiplying them by 100. You're not doing percent. So you have to look at that as well. Just silly little things. Let's see, I've got another, this is going to be kind of stupid. Hang on. Oh, you don't have to see what I was looking at, but I'm going to show you anyway. I was shopping for what the best ramen is on Amazon earlier today. And supposedly it's this Mai Kuali, that's definitely pronounced wrong, Penang white curry noodle. But that seems a little expensive. Anyway, oh, and I'm buying a tuning fork because, like, why not? So here we go. These are all issues that you might see that can affect jitter and shimmer. In fact, what you're looking at here is a database, a speech database that has been used in research to show that jitter and shimmer are, statistically significantly higher in a clinical population relative to normal voices. And you can see that the research in the area is kind of new. It's kind of in its infant stages. We don't know exactly which voice disorders all the time would lead to higher jitter and higher shimmer. There could be some that have higher jitter and normal shimmer. There could be some that have higher shimmer and normal jitter. We don't know yet. There hasn't been a lot of research in the area. But you can see that this person, it's post-irradiation. So they may have had chemo or maybe some sort of, I don't know, a nuclear accident. But that leads to higher jitter and shimmer. Ventricular compression, this person just has hyperfunction of some sort. Post-laryngoplasty, another hyperfunction. Granulation tissue, which is kind of like a node, and other things as well. So this is after removing nodes here. And so you can see that all of these are related to higher jitter and higher shimmer overall, when you just take a clinical population and compare it to normals. But again, like I said, the research is new, and we don't really know. There might be something that we can figure out where some disorders have different values, or some disorders have norm values of their own that we can use to help diagnose disorders. Okay, let me jump back to my PowerPoint and see if there's anything else I wanted to go through. Yeah, okay. Well, so this is a super easy one. I'm going to do it here because I don't think I'm going to have to. Yeah, this will be the last thing, which is what we talked about. It's the harmonic to noise ratio, H&R, or harmonic noise, harmonic to noise ratio. The colon denotes ratio. So you might see it as H&R, you might see it as H:R, you might see it as H divided by R, you might see it as H:(N), you might see it as H divided by N. Harmonics over noise, harmonics to noise is what that means. And then harmonic to noise ratio is how we abbreviate it in our class. But you might see it as all these. And simply, you're looking at the amplitude of the harmonics over the amplitude of the noise. That's it. That's your harmonic to noise ratio. What we looked at before was a noise to harmonics ratio, and they're doing the amplitude of the noise over the amplitude of the harmonics. Same basic idea. Very simple. And what we're looking for there is if you have a ratio less than 20, that's probably a disorder. Right, so less than 20, a ratio that's less than 20 is probably a voice disorder. If you think about that, that just means that this amplitude is, well, it actually means that this amplitude is a lot larger than typical. There's a lot more noise than in a normal voice. And that's just going to bring down um, your ratio, right? So if you had 40 dB of noise over 40 dB of harmonics, geez, over 2 dB of noise, you're at 20. If you had 40 dB in your harmonics and 1 dB in your noise, you're at 40, and that's great. That's non-disordered voice. But if you had, say, 40 dB in your harmonics and then the noise started creeping up there was a lot more noise in that signal, that vocal signal. If you had 4 dB of noise, well, now you're at 10. And if you have a ratio of 10, that's less than 20. So this is a voice disorder of some sort. All right, and with that, my computer, you can see, is starting to go crazy. It thinks I'm touching it when I'm not, and drawing this weird line. And that's the end of the math review. So after you can take a look at this right before the exam, which is coming up at the end of next week. The exam is going to be the same format where I'm going to give you some questions that you have to answer, show your work, upload something, some way that I can see what you've done. And then the rest of the exam is just going to be like I did before. I'm going to pull questions that you've seen before. So you should get those right, because all of your questions, your quiz, your test, come from the questions that you get in your knowledge checks. So those, just do a bunch of knowledge checks and you'll get at least a 50%, right? And then you have those questions that you actually have to like do the math on, and that is the other 50% of your exam. But we're lenient on those, so no big deal. Shouldn't be any big deal. If you have a problem with it, anything like that, email us and we'll help you out. All right. So, like I said, that was Math Review 3. Good luck on this week's content. I'll have a math review 4 up for you pretty soon.